Thank you very much, and thank you for the invitation to participate in this meeting. My talk will be a bit of a break with the previous talks we've had this morning. In fact, I think I've achieved something near orthogonality because I don't apply pressure. I'm not applying uniaxial stress, and I'm not talking about superconductivity, but I am talking about effects that somehow involve lattice distortions on top of magnetism. And so the talk has, in the introduction, I'd like to try to separate two different ways in which the lattice degrees of freedom could become involved in magnetic phase transitions. It's a bit of a fine distinction, but in one case, it's basically an instability driven by the magnetism itself, which then has a concomitant effect on the lattice. And it could be an interesting effect that we'll then want to study and understand. But fundamentally, it's a magnetic instability. And the second type of effect is when we have really a magneto-elastic transition that involves both the magnetism and the lattice. And it seems that these kinds of transitions might not have occurred actually at all were it not for both of those things. Take one of them away, and then the transition doesn't actually happen. So it's a bit of, the talk only involves stuff that I was working on myself over the years, so it's kind of a narrow area because I knew about it, and maybe it'll be interesting for you as well. The introduction is somewhat older work that are supposed to, which I put in to sort of develop the concepts, and then part 2 and 3 are actually examples of those two types of transitions that I was talking about. In one case, in serum cobalt germanium 3, it's really a magnetic phase transition, but it involves quite an intricate form of a lattice distortion that comes along with it. For part 3 is a compound that we've looked at actually for quite some time in strongly correlated electron physics or metal insulator transition physics. These are some new results that indicate that that gives some light into the nature of this phase diagram in that particular material. Actually, now I remember the third thing that was involved in terms of distinguishing this talk from the other talks, which is that this is specifically dealing with atomic scale properties. Some of the other talks were saying we're really kind of at the macro scale, and so in this case we actually are predominantly at the atomic scale. Okay, good. And so then, all right, there we go. Okay, so Magneto-striction. So a slide regarding this point. So many of the problems we're looking at in this talk, somehow we like to think about an exchange Hamiltonian with exchange constants. But the point is that these exchange constants are not actually constant. They depend on other typically high energy physics, and specifically in this case, it's lattice scale physics that's somehow impacting these exchange constants. So just to give kind of an intuition regarding this, regarding this, then we can think of a situation where I have here two chromium atoms, and part of their coordination is an oxygen atom. They may have an antiferromagnetic interaction between them. In this case, it's mostly a direct exchange interaction. But if then in an ordered state I find this pair of spins actually in an antiferromagnetic configuration, that's a low energy state. So this is a bond energy that's negative. And so there will be a tendency in this system to have a slight distortion take place. I think my thing is not quite working. So there'll be a tendency for a slight kind of attraction to occur here. So that these will actually move a little bit closer to each other to further lower the energy of the system. So this is really no different from what you'd see in a ferromagnetic material, where you see a slight change in the volume at the transition into the ferromagnetic state. But when there are competing interactions in the system, you have a different kind of situation that can occur. And that is when, even though the interaction is antiferromagnetic here, you can, in systems with competing interaction, end up with a pair of chromium atoms, for example, which actually, contrary to the local sort of nature of the interactions, end up in a ferromagnetically correlated state. So this is unfavorable for the local energetics. And so you can see that in this expression up here, there's been a sign change in the correlation function, and correspondingly the force that we're calculating, this kind of local force acting on the atoms, actually goes in the opposite direction. So this thing will actually tend to kind of stretch apart. So this already gives you a sense of the kind of interesting microscopic physics that you can have occurring when these exchange constants, in fact, are not actually constant. And so we're going to look for interesting qualitative impacts of these kinds of behaviors, and I'm going to, as I mentioned, try to distinguish two different situations. One situation in which the magnetism is having its own criticality, and then we have, on top of that, an interesting lattice distortions that occur. And then the second one is where these are really combined effects, that it really is a magneto-elastic type of transition. And as an example of the type A situation, I take this case of nickel vanadate that we looked at some time back, actually, together with Tenno Yildirim, who's in the audience, and we had a lot of fun with this compound, but it is some years ago. And so basically, in this compound, again, we have competing interactions between the nickel atoms. I'll say a bit more about that afterwards. And this gives rise to this very rich phase diagram, and it's shown for three different field directions: paramagnetic, what we call high temperature incommensurate state, low temperature incommensurate state, and commensurate prime state. So we won't get into all of the details of this, but the reason that this compound became interesting and was interesting to us is that it actually becomes ferroelectric in this red phase here. So only in the red phase it becomes actually ferroelectric, and you can see it here in the electric polarization along the B-axis of the system. And so we wanted to understand why is it that only this phase is ferroelectric, and the short answer is going to be that in that phase the structural distortion that occurs is one that's polar and actually drives the system into a ferroelectric state. So that's almost just restating the experimental observation, but we were able to actually clarify that by some symmetry analysis I wanted to show. So the basic competing interactions are shown here. Actually, this is the structure. There are two different nickel sites. And this arrangement here is actually quite common and gives rise to a lot of interesting physics in various different systems where you've got a six-fold coordinated transition metal ion with an edge-sharing geometry. And that tends to give rise to both a near-neighbor superexchange interaction, but also a next-near neighbor superexchange interaction. So you naturally have this competition between two interactions, at least when this is an antiferromagnetic interaction. Then you have the competition that will give rise to some sort of a interesting physics. In this case, it's actually an incommensurate modulated ordered state. So we did diffraction experiments to determine these ordered states, and there's a cascade of ordered state. You start off with a second order transition into an amplitude modulated state, indicated here. It's an incommensurate state. But then because of single ion and exchange anisotropies, then actually a second irreducible representation is brought in, which generates an out-of-board component that I've indicated with pluses and minuses here. So actually, this has become a cycloidal state, from an amplitude modulated to a cycloidal state. And then eventually, and we won't talk so much about that, you get into a commensurate canted ferromagnetic state. But just this is the state which actually has the ferroelectric polarization. And you can see from a symmetry analysis that this has to be the case. So this kind of term, which we call a trilinear interaction, is allowed. It has the ferroelectric, the polarization of the ferroelectric polarization along a specific direction, and then two magnetic order parameters, or two components of magnetic order parameters, are required in order to conserve momentum. So there has to be a plus q and a minus q, and then we go and sum over all of the components of the magnetic order parameter and the direction of the electric polarization. And then it's quite easy to see that in the amplitude modulated state, then there's only one irrep present, and so this becomes a mod squared, and then this term actually becomes entirely forbidden. So we cannot have ferroelectricity in the amplitude modulated state. You can also just look at the structure and you see that it actually has a point of inversion. So then it cannot be ferroelectric. On the other hand, in the cycloidal state, there are now two different IREPs involved. There have been two second-order phase transitions. And now this term becomes a more interesting one. And by looking at the table of irreducible representations, one can see that this particular term is allowed. And so you can only have the trilinear term involving electric polarization along the B direction. And so symmetry analysis simply resolves that you can have this kind of multiferroic behavior in that material. So that's the first kind of transition I wanted to talk about. The criticality is entirely associated with magnetism. It is competing interactions, and so you get a distortion of the underlying structure, which can, and it does in this case, have ferroelectric polarization. The other kind of transition I want to illustrate with one well-known and one perhaps a little less well-known example. And this is the case where the lattice distortions actually relieve an underlying frustration that we can identify with the system. Here's the spin 1/2 chain, which perhaps normally we wouldn't consider as frustrated, but I'm going to describe it as frustrated in the sense that a given spin 1/2 degree of freedom could form a singlet with the neighbor to the left or with the neighbor to the right. But in the uniform chain, then there's nothing to say which of those neighbors it should form a singlet with. So that represents a kind of frustration. That frustration is actually relieved when there's when there's alternating dimerization that would occur. Then this pair becomes a stronger antiferromagnetic interaction, this one weaker, and now it's quite clear that this spin should form a singlet with the neighbor to the left, etc. So you've got these two degenerate singlet states that can form. So in that case, actually, due to the frustrated nature of the underlying magnetic state and the compliance of the lattice, we can have this kind of phase transition take place, and it's called a spin-Piles transition. And what's seen in the inelastic neutron scattering, which I'm going to talk about in other parts of the talk, then actually there's a gap that opens up in the excitation spectrum as this singlet state is formed. Now the other example of this kind of transition, I call this spin-Piles-like, that I wanted to mention, is the case of a frustrated magnet, in this case zinc chromate, and it's a spin 3/2 isotropic spin on pyrochlor lattice with antiferromagnetic interactions. And it's highly frustrated. The ordering transition is heavily suppressed compared to the bare interaction. And in fact, prior to that transition being able to take place, if you will, on its own, then there's actually a lattice distortion which breaks the cubic symmetry and induces magnetic order, also inducing a kind of gap, but I don't want to call it an actual gap because there are spin wave excitations at lower energies. But a lot of spectral weight is moved up into a resonant type feature, which sits at an energy similar to the exchange constant. So in that sense, there's a certain sort of kinship between these two types of transitions. A very highly degenerate spin system, which then is actually the lattice distortion points the way to a kind of ordering that occurs in both cases. Okay, so now I want to get to the newer results, which are going to illustrate each of these two types of transitions. So in serum cobalt germanium-3, we'll look at a magnetic phase transition that brings along quite a complex underlying lattice distortion with it. And this is mostly a descriptive study. I don't think we really understand all of what's going on, but I find it quite interesting. So I wanted to have your thoughts on that. So this is the structure. It's a non-centrosymmetric tetragonal structure, and it has actually 3 phase transitions in it, indicated here in resistivity data. It's a kind of a mildly heavy Fermi compound, and it's a very anisotropic spin system, as is often the case with cerium and these kinds of tetragonal structures, and the easy axis is the c-axis. We see that there's strong coupling of magnetism to transport, And our interest here is really to understand the nature of the magnetic phase transitions in this material. This is work that was done by Shan Wu while she was a graduate student at Johns Hopkins, and Chris Stock and Chedomir Petrovic were also involved in this work. And we did the experiments at the NIST Center for Neutron Research. Okay, so I'm going to show you some diffraction experiments that carried out at in each of the temperature regimes for that illustrate each of these phases. So below Tn1, we see the appearance of this 2/3 component of the wave vector. Actually, all of the wave vectors of interest will be along the c-axis. And I should say that all of the magnetism that we're looking at has to do with spin polarization along the c-axis as well. So first this wave vector appears, then cooling further, then wave vectors of a kind of 1/8 actually show up. And what's shown over here, I should say, is this is the in-plane wave vector component. The index is 1. And then here we have these various peaks. And what I'm showing you here is just the intensity along this direction. Okay, and then finally, when we cool to the lowest temperature, we retain this 1/8 kind of commensurate wave vector, but additional peaks occur, and there's a redistribution of the intensity associated with that. Okay, so then that's basically the nature of the magnetism. But then there was another part of it that actually surprised us quite a bit, which was that there seems to also be a pretty significant structural component. And that's why I thought I should talk to you about it at this meeting. So what I'm showing you here are similar plots, but now the wave vector component is actually 0. So these are just for wave vectors along the c-axis. I should say that these are actually difference data in order to bring out the relatively weak features associated with the structural modulation. And so there's a huge kind of complicated story here that has to do with enormous Bragg peaks that are subtracted from each other. And so on average, there's not really intensity here. But this thing is significant, this one as well. Down here, we are again in a region with with some big numbers being subtracted from each other. So this is in the highest temperature modulated state. And then cooling down, this peak actually splits off. And then further, at low temperatures, there's a whole sequence of peaks that also occur there. So this was not actually expected. And a couple of things can be said about that. First of all, the intensity actually grows in proportion to wave vector squared. So things get stronger as we go to higher wave vector transfer. And that already points to a structural modulation as opposed to a magnetic scattering feature, because the magnetic scattering feature satisfies a form factor. But this one is actually growing with Q. Another point is that the magnetism of this compound is completely polarized along the c-axis all the time. In magnetic neutron scattering, we probe magnetism which is perpendicular to wave vector transfer. But here I'm looking along the OOL direction, so I have no component of wave vector transfer in the basal plane. So I'm only able to see magnetism which is spin polarized in the basal plane. And so for those two reasons, we don't expect this actually to be magnetic scattering at all. It seems to actually be lattice related. And then to really check that, we used polarized neutron scattering, where we can specifically project out components of scattering into the structural component and the various magnetic components. And actually, we see in the non-spin flip channel, all of this stuff belongs in the non-spin flip channel, and so is actually a structural component. And there's no component in the spin flip channel to be seen along this particular direction. So this is a structural modulation occurring along the C direction. The lattice parameters don't change, dramatically, but these are really in unit cell changes in the structure that are modulated along with the magnetic structure. Okay, so I don't think I can go through all of the details. It's quite a kind of a complicated story, but what we've attempted to do is actually have a co-refinement of the modulated magnetic structure with the lattice structure modulation. And so here actually shown, this is the highest temperature, and the 8 Kelvin data and the 2 Kelvin data are laid out horizontally here. And these data show Bragg peaks associated with the magnetic component, and these show Bragg peaks along this OOL direction, which is entirely associated with the modulation within the unit cell. And we see that the fundamental wave vector for spin and lattice is actually the same. and that there's a lattice modulation that is associated with the formation of the magnetic order. And to analyze that, what we came up with is a model that gives that relates the displacement of this central atom in the tetrahedral structure away from its center position, and that relates those displacements to the spin configuration in the vicinity. And so, take for example, if you think back to the early picture I showed of two spins that may be in a satisfied or in a frustrated condition, then I can either have a sort of repulsion occurring between these two sites or an attraction, and this can then impact the modulation of the lattice structure. And so, in fact, quantifying that in terms of a magneto-elastic coefficient beta and alpha, we were able to account for the relative intensities of these things in terms of a set of parameters. There's both a parameter that has to do with the pair term, that tells you how much repulsion or attraction will occur for a given set of spins, but also a term that has to do with how much the environment responds to a spin which is smaller than the which is smaller or larger. So the amplitude of the spin actually changes as you go through the structure. So if you look at these pictures here of the spin structures, then you have some spins which are at low temperatures very small, and others which are actually quite large. And where there is a large spin, there's actually there's an impact on the local environment surrounding that large spin. So this is all quantified in terms of these parameters, and so the idea that comes out of this is that of which I think I'll skip this one, though it's very nice, but I'll skip this one. The idea that comes out of this is that this material has what we might call a modulated Neel-Kondo phase. If you bear with me, then the idea is that, and this is actually what the structure looked like. In some places in the structure you have a large spin, other places quite a small spin. And so this is a sort of a quasi-heavy Fermion system, and so the idea is that in some parts of this modulated structure you could actually have more or less screening of the 4f electron site, and that might be part of how this modulated structure is actually set up. So quite a complicated story, we have to admit, in this material. Okay, so then next topic is V2O3. So this is our favorite example of a Mott insulator, which actually has in it a transition between a paramagnetic insulating state and a paramagnetic metallic state. It's quite an unusual thing to have, actually, certainly in transition metal oxides. And the question we ask ourselves is, why is that so unusual, or what is it about this compound that makes it possible to actually observe this, this isostructural metal to insulator transition? Now, there's a huge literature on this compound, and I just want to touch on a couple of things that are important. Here in photoemission, one can see that actually the oxygen orbitals are quite displaced below the chemical potential, and all of the action that occurs at the chemical potential actually has to do with 3D electron bands. And so in cubic symmetry, we would have this T2G to EG splitting to trigonal distortion splits the triplet. This is, after all, a solid, so actually these things are actually mixed together, making it a wholesome, complicated situation. This work was done by this group of people, and this was particularly John Leiner and Suzy Zhang did a big effort on it, and I also very much enjoyed working with Rosa Valenti and Harold Jeschke on trying to understand the nature of the exchange interactions. So this is actually a topic that we'd worked on for some time, and we were always puzzled by the nature of the paramagnetic insulating state in V2O3. And we had seen in previous work that the spin correlations are very short-ranged, even quite close to the transition. So let me just go back to the phase diagram here. really close to this transition, very short-range antiferromagnetic correlations. We never quite understood why that was the case and what kind of picture was going on. These are now the data showing that. So these are slices through momentum space at finite energy transfer and at a temperature which is just immediately above that phase transition. So these are really broad features in momentum space. Why is the correlation length so short? So Rosa and Harold went and actually calculated the exchange constants in the system using density functional theory. And they found that actually the dominant exchange constants were or are antiferromagnetic, called J2 and J6 here. And they actually are both interactions which exist within this honeycomb-like layer. It's actually a puckered honeycomb lattice. But it's a honeycomb lattice, and both of those interactions are quite significant. And as you know, a honeycomb lattice with near and next near interactions is actually a frustrated spin system. Normally, we don't think of honeycomb as frustrated, but when you throw in this extra next to neighbor interaction, it becomes actually frustrated. So the question arose is that could it be that this very short-range nature of the spin correlations was associated with this frustrated nature of the honeycomb lattice? So, of course, in a state with very short-range correlations, one can actually calculate the spin correlation function using something called the self-consistent Gaussian approximation. And Suji Zhang did that using all of the DFT-derived exchange constants, not just the ones in the honeycomb layer, but all of the three-dimensional interactions. And then we compare here that equal time correlation function measured and calculated, and the range and the nature of the short-range correlations are actually quite consistent with each other. Now, this type of theory does not work once the correlation length becomes really long. However, you can use it to get some guidance as to where you would, at what temperature you would expect this spin system to undergo a phase transition. And when you do that, you find that this approximation with these DFT-derived exchange constants would indicate a phase transition at temperature less than 6 Kelvin. So a really low temperature phase transition would be anticipated given this pattern of short-range spin correlations. But what actually happens is quite different. And here's shown the inelastic magnetic neutron scattering data in the paramagnetic insulating state. So quite broad features are seen extending over a large range of energy transfer. This is actually quite similar to what we typically see in strongly frustrated spin systems. Very, very, very broad features both in momentum and energy. A little dull, you could say, but when we see it, we know that we're dealing with some frustrated spin system. But then what happens when we cool just to 100 actually this is at low temperatures, but what one finds at low temperatures is the development of a coherent Magnon type excitation. And when we then take so from these kinds of data, we can then actually refine exchange constants and obtain this kind of calculated spin wave intensity, and we can then compare the exchange constants that one obtains using DFT and using neutron scattering in the monoclinic state, and those are in pretty good agreement. I'm quite impressed myself, and of course there's some that are not entirely consistent, but overall the picture is actually obtained in DFT, and so this gives confidence that this method works actually also in the paramagnetic state, where we don't have the spin waves to check. But the other interesting thing that you notice is that every single exchange interaction within this monoclinic antiferromagnetic state is actually satisfied. So you can see that if you look at the exchange, the sign of the exchange constant and the sign of the spin correlator, those are always of opposite signs. So that means that every single bond is somehow satisfied. This is in contrast to the paramagnetic insulating state, where we have these competing interactions on the honeycomb lattice. And so what's happening here is that in the paramagnetic insulating state, we have a frustrated honeycomb, essentially a frustrated honeycomb lattice. But then as we cool down, the lattice actually deforms, and allows for the transition into this monoclinic state. So the conclusion regarding V2O3 is that the PI state, the paramagnetic insulating state, is actually frustrated by competing interactions on the honeycomb lattice. This PI to AFI transition is an instability that relieves the magnetic frustration of the paramagnetic insulating phase. And I think the kind of message that comes from this regarding the Mott metal insulator transition is that this is something that that I think may be found to come around together with magnetic frustration, in the sense that in order to have this exposed Mott metal insulator transition line, then you have to do something to really suppress the long-range ordered magnetism. And in this case, this has happened by this occurs because of the frustrated nature of the interactions on the paramagnetic insulating state. And then in regard to the magneto-elastic effects, which were the kind of the overall theme in the talk, then this transition becomes then a prime example of this kind of combined effect of a spin-piled-like transition where distortions in the lattice enable the development of magnetic order. So with that, thank you very much for your attention.